Hello. Um, that has a lot of lag. Yeah. Um, I am recording this via Hangouts on the air so that my students, there are 13 of them and only 4 in the room at the moment, can watch. We have a mandatory all hands group meeting, and because these people are, what? Bionic? Where did my Hangout go? This is frustrating. Oh, there it is. Um, okay. Some of them are just sending their hands. Um, Bad joke. All right, so the purpose of this, the meeting usually starts in an hour and a half. The purpose of this portion, um, we probably won't record the meeting itself. Uh, the purpose of this portion is to rehearse for the benefit of the students the talk I'm giving a week from tomorrow at the Old Professor's Bookstore in Belfast, Maine. Um, I feel a little, I don't know, imposter syndrome strikes here. I have never actually conducted a PI type planetary investigation. I have been on review panels for major spacecraft, um, collaborated on papers, read a lot of papers, drunk beer with a lot of planetary astronomers, and taught planetary astronomy for many years. I'm particularly engaged right now in planetary outreach. The All that said, I think I want to share my screen. Um, since I have nobody viewing right now, I won't do chat. But screen share is essential. Um, let's see, full screen. Okay, there we go. Ah, yes, the infinite regression of full screen share. But I actually want to look at this, because I want to open a slideshow. All right, so here's my slideshow. All right, so now we will do all sorts of good fun things like give a slideshow. And if I'm in a place where I'm not talking to a public bookstore type audience, people should, get out the hook, grab me, tell me. Um, the Good afternoon. Welcome to the bookstore. I'm so thrilled to see all of you here. It's a great pleasure to be here with all of you. I've known the proprietor and proprietress for many years. I'm actually rather embarrassed to discover how long they have had a home here. I've known them longer than that, and I only discovered last year that they have a home here. So, um, and I was living here first, so that's very embarrassing. Anyhow, I am a regular summer person in this area for longer than I care to discuss. And it's a great pleasure to share some of what I do when I'm not here with all of you. Um, we're going to talk about what's going on in the planets right now in terms of our understanding and exploration of the planets, because frankly, this is one of the most awesome periods in planetary exploration ever. I want to acknowledge, because I'm myself am, well, I'm a rocket scientist. I work on the vehicles these days, and these guys are all what I would call passengers. Um, but they are critical to this talk. I couldn't have even begun to prepare it without help from all of these people, particularly Emily Lakdawala of the Planetary Society and um, several of my friends with the various missions. And we'll see slides from several of these people, particularly Dr. Russell and Ms. Hallow, um, as we go forward. So what am I going to talk about? Well, I'm going to first tell you about the spacecraft fleet. You guys might want to orient the projector or something. Um, you may need to move it closer or zoom it. Um, okay, so we are. I'm going to tell you a little bit about the amazing set of spacecraft that are now bringing us data. Some of them are as old as 30 years, if they're still working. And I'm going to talk about the problem that poses for NASA because, well, each spacecraft that's working represents a cash flow issue if you want to keep it working. And I'm going to talk about one of the more interesting developments in planetary science in recent years, the discovery of water in a lot of really improbable places. Then I took my lead from our poster for this talk and have focused on Mars and Saturn, largely because, well, Mars and Saturn are where we have the most active spacecraft right now, and the scientific results we're getting are just amazing. This is a thought that is really apropos of right now. I'm going to read this because, well, I'm going to read it. That's what one doesn't do giving talks, but I'm going to do it anyway. In all the history of mankind, there will only be one generation that will be the first to explore the solar system, one generation for which, in childhood, the planets are distant and indistinct disks moving through the night sky, and for which, in old age, the planets are places, diverse new worlds, in the course of exploration. Carl Sagan said that in his book, The Cosmic Connection. Let's look at the data. The process of turning lights in the night sky into beloved old friends began with Luna 2 on September the 14th, 1959. I was in high school. I was a freshman in high school. The first U.S. spacecraft to fly by another actual planet was Mariner 2 on December 14th, 1962. I was a senior in high school. Mariner 4 flew by Mars on July the 15th, 1965. I was at that point, I think officially I was a junior in college at that moment. And actually, I was doing research near here at the Mount Desert Island Biological Laboratory that summer. They needed somebody big, dumb, stupid, and fast to take blood samples from sharks. Since then, there have been approximately 200 planetary missions flown. 55 years have passed. In a few months, we're going to put a lander on a comet, the Rosetta mission. In 54 weeks, we're going to fly by Pluto with the New Horizons spacecraft. Oh, the other thing that happened during this table is that between Mariner 2 and Mariner 4, I audited Astronomy 1 given by Professor Sagan. Professor, sir, we beg leave to report. Mission accomplished. You're very welcome, I'm sure. Now, this is sort of a beginning more than an ending, partly because of the amazing spacecraft that we have en route or on planet at the moment, but also because, well, we have finally begun to solve the problem of observing extrasolar planets. Now, this table was downloaded as of June 12th. The numbers change constantly, always upward. And it depends on which website you go to, because different investigators have different criteria for what's a confirmed planet. But right now, we know for sure there are approximately 1,500 confirmed planets around other stars. And we're getting some detailed data on some of these planets, as seen in the tweet. My reaction exactly, this is a subject? The instrumentation is developing rapidly. And for the people who are graduating with a PhD in astronomy, planetary astronomy right now, here is a whole new field. There are going to be departments formed on the basis of some of these results that never existed. In a year or two, I think I'm going to be reassigned back to teaching freshman astronomy for the first time in quite some time. And I'm going to be back in the situation I was in during the 70s and 80s, where you would print your homeworks for the semester and the start of the semester, and they would be wrong, as in there are no answers to any of the questions on this homework wrong by the time the homework was given out. The Pioneer flyby of Saturn did that to me. I should have known better, because a few years later, the Voyager flyby of Saturn did it to me again. Arthur Clarke said that the data from the spacecraft exploring the solar system represent the only true treasure of humankind. There'll be a quiz on this slide after the show. We've sent, like I said, about 200 spacecraft to various planets. You can see that the Moon has had a huge number. Mars, not quite so many. This is a National Geographic figure, and you can get it from the National Geographic website. And it is actually available in sufficient resolution that you can dive in and read a lot of this stuff in gory detail. The point is, we've been doing our work, and we now know quite a lot. Now, what's happening now? What spacecraft are in orbit around planets or on their way? We have Messenger actively in orbit around Mercury. In fact, they just did a burn to lower the periapsis to about 177 kilometers. Periapsis is the distance of closest approach. So they're really getting, that's kind of daring, but they've been there for several years now, and they've completed 100% mapping. So now they want to get closer to really get a look at some of this stuff. Venus Express is at the end of mission life. It's in fact about to be re-entered to clear out the orbitals. The Japanese spacecraft, Akatsuki, it failed to enter orbit on its first pass, and is coming around again for another try. The moon, there have been a number of spacecraft in low orbit around the moon over the last 2 years that have, the missions were successful, but they've been terminated. Mars has a lot of active spacecraft. The one that's really kind of amazing is Opportunity, which is more than 10 years old. Its design lifetime was 90 days. Now, imagine running a car in a high dust environment. Think the Mojave Desert, frozen, for 10 years without servicing. That's what Opportunity has been able to do. We'll talk about some of the data from Opportunity and Curiosity in a bit. There are 2 spacecraft en route, MAVEN, which is designed to study the history of the atmosphere, and that MAVEN represents my closest association with Mars. I was on the down select committee that picked the mission. And then there's an Indian mission. MOM stands for Mars Orbiter Mission, and it's en route. There are 3 missions sort of running around loose. ICE, the International Cometary Explorer, is about to go back to being its original identity, ISEE-3, doing science at the Earth-Sun Libration Point 1. A group of crowd-funded amateur enthusiasts have successfully put together the capability of regaining control of this spacecraft. It's been flying around basically unmonitored for 30 years. It hasn't been near the Earth for 30 years. Dawn is an ion propulsion spacecraft currently literally being driven around the asteroid belt by a Texas A&M graduate. The woman who did the, this is a subject tweet actually. And Rosetta is a European Space Agency mission which is approaching landing on a comet. We have a detailed look at the Jupiter system planned. The Juno spacecraft is en route. Cassini is in its 10th year of orbit around Saturn. Cassini, budget considerations allowing, is scheduled to remain active until 2017, at which point they're going to be almost out of fuel, so they're going to drop it into Saturn so we don't contaminate any of the moons. New Horizons is a spacecraft en route to Pluto, and the 2 Voyager spacecraft are already outside the solar system in the interstellar medium. I guess this is a somewhat, this table is actually issued, I think, monthly by Dr. Throne. at ESA. Gives you a somewhat more to scale picture. This includes spacecraft that are it includes more than planetary spacecraft. It includes spacecraft for studying the sun, and it does not show the huge constellation of low Earth orbit spacecraft that are there to study the ionosphere and magnetosphere. So we have this massive array of data, fabulous instruments, and the data have been piling up for 50 years. So we really started to know stuff. We're asking detailed science questions rather than, gee, what's the surface look like? And we're discovering that water is very much more prevalent in the solar system than we thought. Now, with all of those spacecraft and all of those data that I just showed you, there's no way that in an hour and a half I can give you a view of everything we've learned. There are a massive number of really good books about these data. Our host has got a few on display. The Planetfall by Michael Benson is fabulous. Depending on your level of technical knowledge, there's a range of books you get. It's a challenging field for a textbook author because, well, preconceptions are shattered every time there's a Deep Space Network data pass. I'm going to try and illustrate some of that. Mercury. Mercury is the closest planet to the Sun. It orbits in 3 months. Now, its rotation period is 2/3 its orbital period. That's a resonance, so-called. But the effect of that resonance is that the solar day is longer than its year. The solar day is 3 years long. Nearly 6 months on Earth. And what's the most amazing thing we've discovered? Well, Mercury has a very interesting property. The spin axis, the North Pole and South Pole, have virtually no tilt to the orbital plane, with respect to the orbital plane. So Mercury effectively doesn't have seasons. There's never a time at either pole like there would be at the South Pole of the Earth where you've got the midnight sun. That means there are regions at each pole that are in permanent shadow. And that allows the temperature to fall quite far. At noon on the day side at the equator, the temperature is 700 Kelvin. The messenger finding that's most amazing is that there is actually water ice in the shadowed polar craters. Here we have a picture of the Messenger spacecraft. Messenger is stabilized by a combination of thruster stabilization and gravity gradient stabilization. But this is also a sensor antenna here. The now there is a web page that NASA maintains, and I didn't show you that. Go back. So this website here, www.messenger-education.org/teachers/wide.php, is a tool for exploring the messenger data about the North Pole. What happens when you go to that tool? What will you see? Well, you start off with seeing the messenger topography plus a control panel. The control panel shows how many layers you have showing. It shows a check for which layer you're looking at. If we look over in this box, we're going to zoom in on this box so that it's going forward. Now, if we look at that box, now, these figures are produced from this wide site by looking at the various choices and clicking them on the left. So this shows a picture of the permanently shadowed regions. These are the regions that we believe never see sunlight. Now, if we add a picture of the radar data from the Earth, taken with the big radar dish at Arecibo, and you can see that the radar currently shadowed regions are actually very low on the radar, and you have these high radar reflectivity regions inside the permanently shadowed regions. Now you can do it, since there's no atmosphere, you can actually calculate the temperature quite easily using a radiative transfer model. And you can see the color scale. I'm not sure it shows in the slide, but that's 50 Kelvin at the purple. So inside the craters, we are looking at temperatures that are predicted to be they're predicted to be extremely cold. Now, if we add in the radar data, you can see that the cold regions correspond to the low regions in the radar data, and they correspond to region where this blue neutron count indicates the presence of hydrogen on the surface, which would indicate the presence of water. The the neutron counter is kind of an obscure counter. That's amazing. How did it get there? The conclusion one has is that it must have gotten there through comet bombardment. The probably hitting somewhere else on Mercury, and then the vapor condensing as ice on the cold surfaces. All right. Second of my strange places to find water. A significant number of the objects in the asteroid belt are fairly large. They're called dwarf planets, technically, rather than just asteroids. Vesta is the second largest asteroid. It's the fourth to be discovered. Vesta lies between the Earth and Jupiter, and its year is about 3.6 times the Earth year. The temperature range ranges from 85 to 270 Kelvin. That's the metric equivalent. That's the temperature scale that starts at absolute zero, and the degree is the same as the degrees Celsius, which is roughly 2 Fahrenheit degrees. The most amazing finding from the Dawn mission is that Venus is wet even today. The color-coded figure in the lower right is actually shows the elevation, and we realize that there's a lot of topography and variation in the surface at Vesta. This is the Dawn spacecraft it's one of two major interplanetary spacecraft to be powered by electric propulsion. The other one was Hayabusa, which was the Japanese sample return spacecraft. So the second object that Dawn will visit, that arrives sometime in the winter, is Ceres. And Ceres is the largest of the asteroids, and very definitely qualifies as a dwarf planet. Sorry about that. It's been a long week. Um, the thing that's interesting about Vesta is that it shows a lot more relief than we were expecting. We were expecting a much more spherical object. This is a animation of several images, and you can see Vesta rotating. Notice the long ditch. That's called a graben, and it's a surprise. We didn't really expect this graben. Almost looked like a walnut slammed together. You can see here how the graben interacts with the craters. This is a heavily cratered surface, and some of the other features that are interesting are the lines of craters that we see in these striped regions here. You don't really have a good explanation of all this. This is new data, and we're trying to figure it out. The tremendous topographic relief that has been found should not have been a surprise. The Hubble Space Telescope has shown us that Vesta had a southern basin, but we weren't expecting two basins, as if there had been two big impacts. As I've indicated, there's a huge amount of relief on the planet. They weren't really expecting the peak, and the large relief, though, was predicted because the rocks are the same strength as they are everywhere else, but Vesta is not very massive. The graben were not anticipated. These small pit chains, which I showed you in a previous picture, were not anticipated. And I didn't point this out, but you can see swirls, which must mean that the regolith, the mega regolith, the soil, if you will, has been actually moved around in response to Coriolis forces. The snowman craters here are really kind of neat. This is a color enhanced picture, and what it illustrates is the fact that the surface materials are very different in different places. Now, there appears to be evidence that indicates there's still water present in the surface rocks. In the crater floors, you have pits, as shown here, as if in the crater floor, volatile material has departed. And we have evidence of minerals that require water to be present for their deposition. Quartz, apatite, and carbonaceous inclusions, and this picture shows some of those. So that people are now expecting to find water on Ceres. And before this, everyone would have said the asteroid belt is dry. If we're going to go live there, for example, to mine, we'll have to bring all our water. Now it actually seems more feasible to go live there and do mining and heavy industry and stuff like that because, well, there's water. And this has all sorts of implications for planetary formation, for the history of the geological history of these small objects. They obviously have had geological history. So these are some of the pictures indicating that there might have been water. These channels are really kind of it looked like there was water there. So we have curvilinear gullies which were once flowing with water. And this is what? And the actual rock that's there is rich in ejecta that are water rich. Got two more objects we want to look at in the outer solar system that have clearly demonstrated the presence not just of ice. Ice is expected. We expect these moons to be comprised largely of water ice. But some of them actually have liquid water beneath the surface. The first one, and the one that's sort of hottest in the news right now, is Europa. Europa is the smallest and second closest of the four Galilean moons. And it is in tidal lock with Jupiter. It rotates in the same rate it revolves. It's farther than the sun than Vesta, so it's colder. Now notice the appearance. The left one is what you'd see if you were looking at it, and this is the one on the right is image processed, and then the close-up. This looks for all the world like a frozen ocean. It looks like a small version of the ice sheets off Antarctica. The cracks, the geometry of the cracks, the way they network and connect. The fact that it's mostly fresh, uncratered surface all says this is ice. Well, relatively new ice. The most amazing recent finding, and this was reported by the Hubble Space Telescope team in December of last year. I think the actual published article is sometime this year. This was quite amazing. We were at the American Geophysical Union meeting, and Twitter has become a major player in scientific conferences. People who are hearing about really exciting findings will tweet, you guys, come to room 2022, which is actually the room this was being presented in. It's amazing. And if you're standing in the corridor outside, say, room 2018, you better get out of the way because there's going to be a flash mob running at you. And so the Hubble Space Telescope reported ultraviolet observations of the spectral signature of water above Europa. Now, this is an artist's conception, a visual light image that fits. They may have been taken at the same time, but it fits the geometry of the observations. Shows Europa hanging just off its parent Jupiter. I think that may actually be either Voyager or Galileo data, and the data processing people have put the two images together. Again, an artist's conception, a Galileo or Voyager picture, and then they have a Hubble Space Telescope UV image. The observations are being done in an ultraviolet line associated with the water, and what we're seeing is ultraviolet scattering of sunlight by the water vapor. And what this actually is the result of an active geyser on the south pole of Europa. But It's an artist's impression in that the two data sets were photoshopped together. The pre-existing visual image and the ultraviolet water image. What's going on? Well, Europa is rather close to Jupiter, and it is tidally locked to Jupiter. But it has an eccentric orbit. And there are two different models. Both of them have a metallic core and a rocky interior with a water ice layer on the outside. I think, if I understand, why is the water maintained? The Europa is in a slightly eccentric orbit, so it's rocking back and forth as it orbits, because it's speeding up and slowing down a little bit. That produces tides. Those tides have friction. The friction has loss. That loss takes the form of heat, which keeps the ice either warmish and convecting or actually liquid. We don't know which it is, and we're going to try and figure out, well, hey, but we suspect, because there's warmth, heat, and energy, and liquid water, that there's a high possibility, there's at least a possibility there could be life in that ocean. So examining the nature of the ocean in detail is the major scientific objective of the first I should say, the geyser observations by the Hubble Space Telescope occurred in December. By mid-January, 6 weeks later, Congress had put a line item authorization for the Europa Clipper mission in the NASA budget. What? Our Congress? That fast? That is encouraging that somebody was paying attention at that level and jumped on it. Enceladus. Most people would pronounce it Enceladus, but hey, C in Latin is hard, or my Latin teacher will rise from the grave and haunt me. I would not wish to upset the good Father Avery in his rest. Enceladus is the sixth largest moon from Saturn, and it has an orbital period of just 33 hours. Note that it's actually about the same distance from Saturn as our moon is from us. It's just Saturn's a whole lot heavier, so it has to go faster. The Saturn system is 9.54 AU from the Sun, and the temperature here is 33 to 145 Kelvin. And this is a tiny little thing. It has a radius of 252 kilometers. Now, it looks like a snowball. These regions here with some of these crevasse features, these features here are called tiger stripes. This looks like an active glacier. The crater density isn't anywhere near what it should be to if the surface was actually primordial. This is geologically active, recently renewed surface. The other thing about Enceladus is that it's in the middle as we'll see when we get to the Saturn system, of the E-ring. And here we go. There's Enceladus, and here's the E-ring. The E-ring actually turns out to be ice crystals from the condensation of the geyser exhaust from Enceladus. I think it's interesting. Dione is the 15th largest moon in the solar system, and it weighs more than all the other known moons, all the other known smaller moons combined. These are a very interesting family of objects. And the 9-year Cassini mission has taught us a huge amount about them. So we have a contrast here between an old cratered surface on the upper right part of Enceladus and this looks for all the world like fresh glaciated ice. We have these large-scale organized fractures over here. The south pole of Enceladus is sort of on the lower right of the picture in this photograph. Now, this is very interesting. These features here, this parallel graben or parallel crevasses, fractures, faults, are unlike anything on any other object. One of the things that's totally fascinating about the solar system is the way in which each object is unique. One of the things that's fun about teaching solar system astronomy these days is you can do slide ID questions. Now, dealing with these somewhat featureless white bodies, I have fun with that. I gave a slide ID question to a group of freshman astronomy students about 20 years ago. Actually, it was more like 30 years ago, during the Phi Slamma Jamma period when the University of Houston had national championship basketball teams. You guys weren't even born. I had this question. The slide on the screen is Venus, Mars, Titan, Triton, or a basketball. Now, I have slides of all those objects, and depending on year and whether it's the first hour test or the final or whatever, I would just pick one of them at random. I have slides of all of those objects, including some very carefully taken slides of a basketball, brightly side-lit against a black velvet background. Some of them might even have a golf ball in orbit. And if I'm being mean, I can show them without the logo being visible. Or if I'm being really nice, it says right on it, Wilson. 10% of the students, on average, get this question wrong, which means that out there somewhere, 10% of the population of the United States thinks the solar system has a planet named Wilson. I worry about us. Now, this is an observation of Enceladus from a distance, and what we can see here in this picture are what appear to be geysers, actual water jets. The geysers of Enceladus were discovered quite a bit before the geysers of Europa. This is a color-enhanced picture showing images of the geysers in a sunlit limb. of Enceladus. This is a map showing the tiger stripes and the surface temperature, or composite image. Now the tiger stripes look kind of like the mid-ocean ridges on the Earth, except they're not quite so vertiginous. And we think that this is where the water is upwelling and creating new surface on a steady ongoing basis. The cracks are being produced by tidal stresses of one sort or another. But you could note that there's a very substantial hot body near the surface in the tiger stripe region. This is one of the tiger stripes. The tiger stripes, for some reason, are named after Mesopotamian cities. This particular stripe is Baghdad, and it's shown in a very highly side-lit view, and the thermal imager, the infrared thermal imager data are overlaid. You can see it kind of looks like, wow. This wouldn't actually look like this because the temperatures are actually very cold. What we seem to be showing is that each of these stripes is a heat escape region. Now, besides being a heat escape region, if we take the geyser images and overlay them, now this actually also shows where the Cassini spacecraft did a fly-through, and locations A, B, C, and D are where the water and particulate counts in the appropriate detector is maximized. So the tiger stripes are in fact the source of the geysers. Why? Enceladus is in a tidal resonance, or is in an orbital resonance with Dione. Enceladus orbits twice for every orbit of Dione. That means that Enceladus orbit is somewhat has a higher eccentricity than you would expect. And the result of that higher eccentricity, the planet, as it is in close to the sun, is rotating more slowly than it has to, so it appears to, as it goes around, it appears to be falling back on its phase locking with the planet, and then as it gets to its more distant part of its orbit, it apparently speeds up, so it rocks back and forth. Well, the tidal bulge that's being produced by Jupiter is rocking back and forth in the frame of reference of the planet, or the moon, and that produces a huge amount of friction. That friction is quite enough to maintain a reservoir of liquid water under the ice cap. So that's the water tail. Let's talk a little bit about Mars. I'm probably not going to get all the way through this talk. I over-prepare. I have 148 slides for 90 minutes. We have a lot of active missions on Mars, and the one that's currently most exciting is the Curiosity rover, but the Opportunity rover and several of these orbiters are still active. There have been 42 missions to Mars. Mars is a killer planet. We've only had a 50% success rate. That's gone up a lot in the last decade. The first time I prepared this slide, it was more like a 33% success rate. The late 90s were what we call the dark time in the Mars program. There was a certain speculation that there was somebody on Mars shooting them down as they came closer. So we have a number of spacecraft. There have been quite a few, and I'm not going to tell. I have a presentation that talks to all of them. It's a 6-hour presentation for teacher training. You don't want to hear it. The Mars Global Surveyor, these pictures of what look like water gullies in the wall of a crevasse. One of the interesting observations. Now, Mars Odyssey is still orbiting. It's the longest-lived orbiter still in service. The orbiters serve two purposes. They're continuing to do their science. They provide the rovers with detailed overhead imagery that gives them guidance as to, well, you want to turn left here because if you turn right, you're going off a cliff. Kind of guidance. They also serve as data relays. They have a radio that can contact the rovers, and then they have much more powerful radios and antennas for talking to the Earth. The rocks and minerals, the salt is volcanic. Clays and carbonates are sedimentary, indicate that at least one point in time there was enough material there. Mars Express was partially one of the failures. It arrived with a lander, the ESA, mostly UK lander, the Beagle, and the Beagle crashed. We're not really sure why. NASA has a radar mapper on Mars Express. And here are some of the pictures. These pictures are of the summit caldera on Olympus Mons, and showing detail of the wall and the details of the crater floor. Olympus Mons is the largest volcano in the solar system. It's enormous. Olympus Mons is roughly the size of the state of Arizona. And here some of the kinds of data that we've had for some of these orbiters. They can do subsurface radar sounding and establish the relationship between this is a view of the South Polar Cap, and so you're seeing the rock layer under the water ice. The MRO has kind of instruments needed for planning landings. It's got high-resolution cameras and high-resolution mapping detectors. There are two operating rovers on the surface of Mars now. Opportunity was one of the 2003 Mars Exploration Rovers, or MERS, and they're searching for, basically they're looking for soils that indicate that there was once water present. They're doing soil chemistry experiments more than anything else. Here's the family portrait. The little guy is Sojourner. That was landed around 2000 or the late 90s. The guy on the left that's a mock-up of either Spirit or Opportunity. And the one on the right is Curiosity. It's the local mock-up. Um, they've never been together like that on the surface of Mars. These are um, engineering models. They actually work. They're used for testing command sequences, and this picture is taken in what's called the JPL Mars Yard, which is a basically an interesting landscape architecture challenge. Make it Mars. So we can see here where most of them, for orbital dynamic reasons, have all of them have landed. No, most. There's one that's landed near the pole, but all the rovers and most of the landers have landed near the equator. So the two first landers, the Viking landers, which landed in the bicentennial year of 1976, um, and we're primarily looking for life. In a fit of irony, they had what they found instead was a strongly reducing environment. It was more reducing, chemically reducing, like lye is a reducing agent, um, than they were expecting. But so they got a false chemical signature that fooled them for a while because it met their pre-launch criteria for life detection, but it didn't seem to be repeatable. They finally decided that this was just a highly reduced surface encountering an oxidizer. And you can see where the um, various spacecraft have landed. Curiosity is in Gale Crater, marked with a star. Um, Viking 2 and Viking 1 are as shown. And Spirit and Opportunity are the craters indicated. Some Spirit pictures. And you may have seen some of these in the news. The Spirit did a number of studies of this big basaltic rock, volcanic, called Adirondack. But then um, you might be curious as to what that is. That was unearthed by the rover's own wheel. That's gypsum. Now, some of the detailed micro studies that they did, um, these so-called blueberries, which are hematite nodules. Hematite is mud, is a mineral that's deposited by evaporating water. It's an iron-rich mineral. That's a pretty good clue that at some point there was liquid water. And then the stratigraphy looks like these were sedimentary rocks, including the mud, that were deposited in the Escher Rock area. Um, Now, in 10 years, 6 or 8 years ago, when Spirit and Opportunity had only been going for 2 or 3 years, you know, the people who gave Spirit and Opportunity talks said, you know, the uh, an energetic graduate student could have done everything the rover did in a day and a half. That's not so. It would be a week or two of actual field geology to do everything that Opportunity has done over the years. You can see the extensive trek. Um, Zoom in on some of the detail. You know, Cape York is a cliff overlooking one of the craters, and it has a lot of exposed strata. So they've really been able to look at a lot of the stratigraphy of this region very carefully. And I'm sort of sounding like a broken record. And this is where they are now. Moving in on a region called Santander Point on the this is a crater rim, and you can't really see it, but it's a very large crater rim. The crater's to the right. And these are some of the pictures that Opportunity has taken over the years. One thing to realize, this looks like an enormous cliff, that feature in the center of the picture. It's 3 feet tall. You know, comes to here on me. These are actually relatively small features seen very close up. This is part of what they've been looking at. Victoria, this is the Victoria crater region. It went down into the crater on that steep slope and then came back out. As the years went by and they got past their, well, we've been there for 4 years now, we only expect to be there 9 days, they got, what did they have to lose? So they started to take some substantial risks to really investigate some of these features. I think I will skip Phoenix. I'm running out of time, and it's clear I'm going to have to edit this or give the talk when I'm not falling asleep. 4 o'clock in the afternoon on a Friday, challenging to everybody. So the Phoenix lander we won't talk about. The Phoenix lander stayed in one place, and all right, so here's Curiosity. And Curiosity landed, when Curiosity landed, I was actually in Maine, where I'm going to be giving my talk. They have a huge variety of cameras. This thing weighs 1.5 tons, and it's atomic powered. Most of you have heard about the 7 minutes of terror, the landing process. I was on the engineering panel that reviewed and approved the mission that's in flight now. And I know how conservative these people are. I can't believe they got the landing scheme through the technical management and cost panel. It boggles the mind. But if you've ever had the privilege of listening to my colleague Adam Stelzner, who is the chief re-entry and landing engineer for JPL, they didn't really have a choice. The spacecraft's too big for the bouncing balloon method that was used for Spirit and Opportunity, and you really want to keep the rocket exhaust away from the ground you're going to be landing on for a whole bunch of reasons. So they now the re-entry process, first off, they got rid of the propulsion system that was used during cruise, and they got rid of some weights that kept the spacecraft balanced during cruise. Now, the balance that they wanted during re-entry was very different. The spacecraft was actually flying. It was getting appreciable lift and navigational guidance from its interaction with the atmosphere. And so there you go. The first known flying saucer in the solar system was from Earth. And the most amazing part is the sky crane. After they wanted to get the chute away from the spacecraft, the atmosphere is so thin you really can't get to stop on the ground with a chute. And if you did, you'd have such a large chute, it would just all come collapsing down onto the payload and tangle it up. So they need to get the chute away. So they just cut it off with back shell separation. Um, and the what happened is, as the powered descent was going on, they were also lowering the rover, deploying the wheels, and when the rover itself finally touched down, then the cables released and the rocket motors took the landing stage away. There's so many things that can go wrong there. It's amazing. It all worked perfectly. If someone ever tells you that something's impossible, point at Mars and tell your audience firmly, sky crane, your argument is invalid. If we can do this, nothing is impossible. Nothing. Now, one of the other orbiters actually got a picture of Curiosity on the chute. This wasn't an accident, they planned it. Imagine the planning that takes. This is the heat shield that has been blown off the rover. This is sort of a mid-disintegration selfie. You know, imagine Van Gogh taking a selfie of his ear going away. Now this is an interesting picture of the error in the landing oval. This is what they ended up with: the heat shield, the sky crane, the back shell, the parachute, and Curiosity. Pretty much according to plan. And this is Curiosity's first selfie, and it's done with one of the mass cams. And you just, it takes a certain amount of stitching a whole lot of small images together to produce this image. Then they did a panorama. They did a lot before they even moved, because as far as you know at that time, your first observations may be your only observations. That was 2 years ago. Now the real destination is, at this point off in the distance, it's the mountain in the middle of the crater called Mount Sharp. Really? Mount Sharp? Mount Sharp is a bizarre feature. It's a sedimentary rock feature in the middle of an impact crater. How the hell did it get there? What was it? What is the geological history of this object? We have no. We have models. We have guesses, but we have no proven results we can speak to. Here are some of the details. By now we're getting closer, but these were taken 2 years ago. I actually know some of these people. One of the young ladies who did this for the first 60 or 90 days was at the time a graduate student at Texas A&M, and she gave the awards talk at my Mars Rover Outreach event for several years. And she is a charming woman, wonderful scientist, and rather short and slightly built. And somehow this language here gives you the picture of somebody who, well, he had a choice. He could be a nerd or a linebacker. And so I would introduce her with this slide and then bring her on stage, and here she is. And all the 13-year-old girls in the room would go, I could do that. It was amazing. And the goal of the project is to learn if Mars could have supported microbial life. What are the key findings? Mars has lost much of its atmosphere. The escape was to space, not to the ground. The light argon isotope was also lost. We've detected a bunch of whirlwinds. The rocks in the first year of Curiosity's explorations were found to be streambed gravels. 3 pavement-like rocks were examined in detail. The conglomerates, the rocks that are bits of other rock mushed together and stuck. Now these stream durations are minima. It was at least a meter per second. It was angled to hip deep or more, and it lasted for months. Could be much more. This is the 1-year anniversary panorama taken with a feature called the Twin Cairns. If you ever wonder where all these weird names come from, just go to the bar with some of these people. The scientists and the engineers who are running the project come up with these ideas, probably by just sitting around listening to their toddlers. I don't know. It's pretty clear now there was an ancient lake in Gale Crater. And this is pretty much what we think it looked like once upon a time. I got started about 10 minutes late, so I'm still good on my 90 minutes. Now the thing here is that you can actually see the rover. There's the rover right there. You can see the rover and you can see its track. This is the landing region, and it landed over here. See the discolored rock. There's the track heading over to here. It's one of the first rocks that got examined carefully. We now have much more time under our belt, and this is sort of a quiz. Can you spot the rover tracks? Can you even see the rover? I think this may just be tracks. Anybody? You guys go point your fingers at the rover tracks? They are in here. I found them earlier. There you can see it. And so the terrain in this region is very difficult, and this started to beat up the wheels. The tracks go off this way, and has resulted in some interesting changes in mission strategy. You can see the tracks in here, and they kind of go around and up. Challenging terrain. A region called the Rock Nest, they took a 1 billion pixel view, and it's interactive, so you can zoom in on almost everything. More of an update. It's on the road to Mount Sharp. I'm going to have to cut this down. I got a lot more stuff to go when I get to Saturn. Lately, until very recently, you've been hearing a lot in the news. If you follow the news on the Twitterverse or wherever you get your spacecraft updates, there's been a lot of buzz about the Kimberly. And this is the current position as of, sort of Christmas time. Let's see, 590, and we're now at 660. So that's 70 days ago. This is when we were at the Kimberly. So it was just after Christmas, just in midwinter. And these are some of the terrain variations that we're seeing as we're driving along, trying to get to Mount Sharp. And you can see these combination of craters and various erosion features. Now there's now a bigger hole in one of the wheels, but you can see the wheels are beginning to take some grief. You can see some dents and scrapes, and there's actually, if you look carefully in this picture, there's some holes. There's now a big hole in one of these wheels. So they've rerouted Curiosity to avoid some of the more rocky terrain and spend more time driving on more sandy terrain. Well, that has its own risks. They weren't really sure they could get over this without getting it totally bogged down. Spirit got bogged down in sand and never got out. This is what's called Dingo Gap. And they weren't going to go over it at first, but they decided that going over terrain like you see on either side was beating up the wheels too much. So they went straight through, and we can see they got through successfully. That was several months ago. Now, one of the other things they're doing, because it actually beats the wheels up less, is driving backwards. Now there we've gone on to, this is sort of the close-up of the region around the Kimberley. And so that you can see we're going to be looking from the yellow dot toward the black arrow. And you can see the difference between what it looks like on the ground and what it looks like from on orbit. Some of those features seem to be a lot more, well, mountainous. And we see differential erosion at work. Most of the erosion forces on Mars are actually wind-blown dust. Aeolian erosion is the dominant erosion feature on Mars. Where's our mandate? It's 5 o'clock. Everyone should be here. So we're now looking for drill target sites at the Kimberley waypoint, and they're kind of working their way around. They ended up doing a lot of drilling kind of over in here, and they've now moved on this way. This is in a rock called Winjana, and it's at the Kimberley, and you can see the spaces here where after they drill the hole, they then zap the fresh rock on the whole wall with the ChemCam laser, and then do spectroscopy on the puffs of gas. And the laser cannon has now shot several 100,000 shots. That's the good news about a laser cannon. As long as the atomic power holds out, they can shoot up the rocks to their heart's content. Okay, so there was the Winjana rock that we just looked at, and this is really part of the Kimberley. You see, they were in 589, and they've come around this way, and now they've gone on. This was June 12th, so they've gone on further to the left since then. Now this is the picture on June 12th. Somewhere in here is the actual rover. Anybody see it? Right there, I think, something like that. You can see the tracks as it grinds along. So the Curiosity has an extended mission. I'm going to have to cut some of this stuff so I can get to Saturn. Not quite sure what. It's a good thing I've done a practice. So we're in here now, and they're actually, notice how rugged. I mean, this is actually a canyon between where they are and Mount Sharp. But the entry point that gets them into Mount Sharp is this region here. There's considerable concern that the wheels aren't going to hold out. That terrain is getting really rugged. This the difference between what they're driving through and where they're going. And that boulder there is the size of Curiosity. So it's going to get interesting. Hang in there. And we're looking for water. The future missions, Maven is en route and it will arrive sometime in the fall. InSight is scheduled for launch in 2015. It's a stationary lander designed to do deep exploration drilling. This is a picture of Maven. This is MOM, the Indian mission that's en route. And this is what an artist's conception of what the InSight mission will look like. And I'm not going to get to show you much about Saturn. I'll just flash through the pictures. I gotta speed this up. Because it's time to stop the hangout and let Diego and team conduct their payload design review. Oops. That's the storm on the North Pole of Saturn, which is kind of amazing. Titan is, well, it's nearly half the radius of the Earth, and it's enormous, and it has 1.5 times the Earth's atmospheric pressure at the surface. The atmosphere is made of nitrogen and methane. It has oceans, factual oceans. The oceans of Titan contain more liquid hydrocarbon than exists on the Earth. The oceans are a mix of methane with a small amount of ethane and saturated solution of benzene. Really good for your cancer health. There's Titan from a distance. Now, this is in the infrared, and you can start to see features. There are lakes down there. There was a landing by a probe that lasted for several hours after it landed, called Haugens. I apologize to all the Dutch speakers who just winced. Glottal stops are not a native phoneme in English. This is a region on the surface of Titan. This is a combination of infrared imagery and radar imagery. And the Xanadu region, this sort of crater-like feature here, is where the lander came down, and the coming in out of these images have been colorized by somebody who's good at it. But this is what the Hawkins lander saw while he was on the chute. This is sort of a artist's conception, and with an actual image on the left. There are oceans. There are oceans. There's a radar map of the oceans and the infrared map of the oceans. I think this is a radar map, not colorized, of Ligea Mare. Here's Kraken Mare, Hinksum Draconis. They're amazing, the science is going on now. Notice this very narrow strait here. Oceanographers, Titan oceanographers, are studying things like the rate of tidal erosion and the effect of tidal erosion on the geography of that strait. Fascinating. This is Ligea Mare. Ligea Mare has its own fascination. I'm tempted to caption this slide OMG whales, because one pass, T92, where are we looking? We're looking right in here. And in T92, in that region, there was what appeared to be islands, except they disappeared. Now, you can see islands appearing because this is spring in the northern hemisphere of Titan. All sorts of things could be going on. Changing water level, all sorts of changing methane level, whatever. But to have a transient feature, anomalously bright transient feature. I listened to this talk. It was given for the first time by Hofgartner at the Lunar and Planetary Conference in the Woodlands. And a colleague of mine who will remain nameless, at the end of the talk, tweeted, OMG, whales. Now, that can't be. There's plenty of free energy, but no oxidizer. So there's no way for a metabolism to develop. But the data are consistent. That could have been a pod of whales producing we have no idea what produced those data. We may never know. But it's a fascinating anomaly. We're running out of myths. The mountains on Titan are named after mountains from Middle Earth. The planetary program is in trouble. It's underfunded. It's underfunded by a tiny amount. You know, $50 million would make all the difference. And that's a small fraction of NASA's budget, much less the US budget. We're about to lose a very bright, very energetic, very, very well-trained and fabulously inventive generation of planetary scientists because they're going to go off and get tenure track positions and then get no funding because the funding's gone. This is the golden age of planetary exploration, but gold is the color of autumn. One thing you can do, besides writing your Congress being, we don't want to be speciesist here, is join the Planetary Society. And like Professor Sagan said, the planets are no longer distant dots. They're paintings on your living room wall. Thank you. That was spot on 90 minutes, but I was hurrying at the end. Okay, so now what I need to do is stop sharing my Hangout. Now we want to go here. Well, okay, everybody. We have no live viewers. Well, whatever. I will stop so that Diego can conduct his meeting, and you're going to switch to your computer, and you're going to switch to your broadcast, correct?
I'm just doing a Google Hangout right now, not a broadcast.
Yeah, okay, those of you who are in this team, will go to regular Hangout. So, signing out until next time.